Okay, guys, we're going to look at something. It's the last concept. So there's four concepts that we're going through in this chapter 12. The first one is look at the rate, the initial rate versus initial concentration. And you would take a look at that. That was kind of what you did in your lab. And you're trying to look at your concentrations. And as they change their concentration, either getting lower or higher, then you can see the effects on the rate. And then you can get what's called the rate law. It's called the differential rate law, but it's the rate law. And you did some problems on that. You did like 3 problems. I gave those back. It was like 14 points. The next thing you did was we looked at the idea of looking at changing concentration over time. So we looked at time and then the change in concentration for time. And by doing that, we were able to figure out an order based upon the graphs that we got out. So yesterday I gave you an assignment to do 3 problems where you had to plug in the numbers, get the graph, decide what order it was, first, second, or third. Then you had an assignment you turned in a couple days ago that took the integrated rate law and used it to figure time, final concentration, initial concentration, all those good things, right? Questions on that? I mean, that's what we've done right up to this point. So now I'm going to talk to you today about this thing called a reaction mechanism. So what's a reaction mechanism? Well, it is the series of steps that take place, theoretically, that take place at the molecular level when we take a look at the individual steps of a reaction. So a lot of times we just have the overall reaction, and that is the final. That's the sum of all the steps. So when you got a reaction mechanism, you're going to have a series of steps that can be possible. It's kind of like, I don't know. Do you guys do proofs? Or have you done proofs before?
Yes.
I know when I took geometry, I did not like that. I had so much trouble with proofs when I was in high school. And you would have to prove kind of like a final equation, right? Or how's that work? You guys?
You've got like an initial and like a final, and you have to prove that you can work the initial to the final.
Right.
That they're equal.
Right.
Whatever.
Right. So it's kind of like Hess's law is kind of like that, isn't it?
Mm-hmm.
Yeah.
Remember, because Hess's law, you go through to find out the final reaction, the heat of the overall reaction. You took the individual reactions and looked at it that way. So these are kind of like Hess's law in a way, but these are theoretical. They can't really see the reaction, and they're also based upon experimental results. And so they're just saying, hey, we think this reaction mechanism is this, and they can do some experiments with it just to see if it's a possibility or not. Okay, you'll kind of understand what that is later on. So we're going to look at what's called reaction mechanisms today. This is basically the last difficult concept to go through, and I don't think it's that difficult, but then we've got one other thing I won't get to today, but I'll get to tomorrow. And we'll do it tomorrow. And then we'll be done with chapter 12, basically the information that you'll need to know for a test. So there's a reaction mechanism, and all it is, it's describing the series of steps for the overall reaction. So to be a good reaction mechanism, it has to follow some certain protocol for it to work. And you can tell if it doesn't work or not based upon how the experimental results compare to the written reaction mechanism. Okay? So, if you look on page 490, they have these things called elementary steps. And then the elementary steps are the steps, the series of steps that take place. So each of the reactions that we write out, the individual steps are called elementary steps. And they talk about this thing called molecularity. And it's defined as the number of species that must collide to produce a reaction. So there's different types of collisions that can take place. That's what they're saying. A reaction involving only one molecule is called a unimolecular step. So that's basically having something decompose. So if it's only one molecule is in the process of this reaction taking place, that's called a unimolecular step. Reactions involving collisions of 2 and 3, so 2 species. So a unimolecular step is the same species hitting one another. Okay? A bimolecular step is 2 different molecules or species hitting one another. Okay? And then termolecular, that doesn't happen. That's very, very rare. 3 hitting simultaneously. They all free hit. I mean, for the odds for that to happen, but they're also moving very fast, and it can happen, but you could have 3 collide at one time. Okay? So 2 collisions of 2 the same, unimolecular, 2 different ones, it would be bimolecular, and then 3 together is termolecular, and that doesn't happen very often. Okay? So we're going to look at what we call a reaction mechanism here in a second. Okay? So I'm going to show you a reaction mechanism, and we'll just look at it to see what it really says. So the steps can be categorized as slow and fast, very slow. And that's relative to one another. So this reaction, the first elementary step, so this is to be the first elementary step right here. They're saying that's the slow part of the reaction. Kind of like being on an assembly line. And maybe there's a slow process on the assembly line in which to crank out a product. And so they want to crank out as much product as they can, so they probably want to, maybe make that part of the line, more people on that part of the line, or try to quicken up the process somehow to make more of the product, less amount of time. Time's money. Okay? So if you've ever, X mark is based upon an assembly line, right? Cranking out a mower, maybe a line can put out 50 mowers in an 8 or 10 period of time. And that's painting it, putting all the parts on, the engine in, all the deck on, all that kind of thing, process. And so there's probably fast, if one part of the line breaks down, then basically the line shuts down because it can't continue. Okay? So we have a kind of a line happening here, and this first reaction is looking to be a bimolecular, right? Because these two are colliding, and when they collide, what's happening? So when they collide, what happened? They bonded. So these two, nitrogen monoxide and chlorine, collided. They collided with enough energy that they held together. Too much energy, they'll bounce off one another. Not enough energy, they won't bond. That's called an activation energy. We'll get into that tomorrow a little bit. So then they bond together, and guess what? Another NO comes along, bimolecular, hits the NOCl, and when it hits the NOCl, it makes it makes two of them. Okay, and that's the fast part of the reaction. So once the NOCl2 is produced, then this is really quick, this process of that hitting the NOCl2 and producing 2NOCl. That's the fast part of the reaction. Okay. Now, what we can do is we can write the overall reaction if these are the two elementary steps that make up the overall reaction. So we've done this before, I think, where we've added, right? So what can we get rid of? What cancels out? NOCl2. Okay, later on we're going to call this the intermediate. An intermediate is made during one elementary step and used up in a second elementary step. So an intermediate never lasts. It's never going to be part of the overall reaction. It's produced by one elementary step and then used up in another elementary step. And that's what we call an intermediate. Okay? So then this would be 2NO gas plus Cl2 gives 2NOCl. Questions you guys have at this point? So one thing that the reaction mechanism has to do is when you look at all the steps and get rid of all the intermediates and catalysts, we'll know what a catalyst is here in a second, and you get rid of all those, then you get an overall reaction that should match up to the reaction that you're trying to write a mechanism for. So if they have like, hey, this is the mechanism, this is the reaction, overall reaction, does this mechanism fit? And you'll go, okay, I'm going to go ahead and get rid of the intermediates and the catalysts, and write the net, kind of what we say, the net overall reaction. And if it matches up, you go, well, that's a good mechanism by looking at that. But it also has to prove the experimental order. So let me tell you how to find an order. The order is based upon the slowest reaction. And what you do, the slowest reaction can have, you don't count a catalyst. Now this doesn't have a catalyst, but you won't count a catalyst. And what you do is you'll say, for the example this one, you'll say rate of the reaction is equal to K. And then you do the concentration. Well, it's based upon your slowest reaction. So it would be NO, and it would be a first order, because you only have one NO there. So if I had two NOs coming together, that would be NO squared. So, which means if I had my first reaction is unimolecular, I have NO plus NO makes 2NO, for example, then what will happen is that'll be NO squared, because I have both of those concentrations in the slowest step, and that would mean an order of 2. Now I also have Cl2 there. Okay, and so that would be the rate law for that reaction mechanism. Does that make sense? That's the rate law. So we'll do a couple more of these. But before we do that, I want to show you how this fast step is dependent upon the slow step. So this can go as fast as you want, but it's dependent upon the slowest step. And because it has to make the NOCl2 before we can have a collision with NO and NOCl2. Yep.
So like with that bottom one, if you were doing the rate law for that, and like you don't have the original 2, so that would be NO squared, right?
Yep.
Okay, just making sure.
Yep.
Is it squared because of the 2 in front of it? Because you have 2 and L?
Yep.
Okay.
Because I have 2 of these. Yep. So because I have 2 of them and just 2 moles of it, I guess you could say. Now, if I change this up, and let's say that we change this up, and I said, no, that's not right. It's probably shouldn't erase that. But let's say that it was, the second one was the slow one, and the first one's the fast one. So what you do, if that's the case, your intermediate still will not be part of the overall reaction. I should have left the overall reaction, but I'm just trying to see. Now this rate law would not be right. Because what we would do is we'd have NO, it would be NO, because both of them, this one was fast and this one was slow, so you include the fast in your rate law when you write it. So that would be NO squared and then CL, or NO to the second order and CL2. Because what you'll do, you go down, if the second step is the slowest step, then you include the first, because it can only go, it's only going to be used up as the second one goes. Okay, I'll show you that, because that's why I wanted to show you that. All right, so I'm going to go ahead and show you. I need some help. So what you're doing is it has to agree with two things. It has to agree with the overall reactions, which I'm not giving you. I'll give you one here in a second where you can prove if it works according to the elementary steps and the overall reaction. Okay. So the overall reaction's what? 2NO plus O2 gives you 2NO2. Is that what you got?
Mm-hmm.
Okay, the intermediate would be, this would be the intermediate. Okay, and then the rate is equal to K times NO2 plus O and O2.
Just O2.
Okay? Questions? Okay, let's have you do one. Let me talk to you a little bit about catalyst. Okay, a Western ranch owner. Okay. One person got it. Okay. A catalyst is in a reaction is something that is in the first is a reactant in the first elementary step, and then a product in a second or third elementary step later on. So a catalyst is not in the overall reaction, and it is used a lot of times to speed up the reaction or lower the energy for a reaction to occur. So we call them catalysts. If we would have did the last lab, you would have had a catalyst, I think it was copper sulfate. that would have sped up the process of the iodine turning, or the reaction turning color. And there was one in that, and we did that last year, but we were a little ahead from last year, so we didn't really need to do it. Okay, so the catalyst in this first case is what? So it's a reactant, but then it's also produced and then falls out when you go ahead and add them together. It's chlorine. So chlorine is your catalyst here. So this is chlorine, and that would be your catalyst. And then your intermediate is ClO, right? Okay? So in that reaction, if we would add them together, that would be O3 plus O would give you 2O2. Okay? Next one, which one's your catalyst? NO. So nitrogen monoxide is the catalyst there. And do you have an intermediate? Yeah, you got NO2 is your intermediate, right? So those would be canceled. And then catalysts and intermediates cancel out. And then we got O3 plus O gives you O2. Or 2O2. Oh, they're the same. So it looks like decomposition, but it has nitrogen monoxide as the catalyst in this one, and this one was chlorine as a catalyst in that one. Okay, so ozone decomposing would be, NO would speed up the decomposition, and same with chlorines. It would increase the rate would go faster. Okay, questions you guys have on that? Anything? Okay, well, I think I've given you enough information that you can start going through these. I got one more. Let me see if I can find it. Okay. So I want you guys determining which of the following is the rate determining step. I haven't put a fast or slow there. I want you to tell me, is A the rate determining step, or is B the rate determining step? And then also prove if these elementary steps match up with your rate law. So go ahead and determine which one's your rate determining step, and then if the overall reaction works out right or not.